Hey guys, so last problem, chapter 10. I think you're going to like this. So, a lot of you have told me that you've had some problems with figuring out just how to set up some of the questions. I thought that this would be pretty good. It's not too hard, but I think it takes into account a bunch of the things that you'll see that are trickier in some other problems. So if you're following along in Taylor, it's 1037. That is what I am looking at. So here we go. This problem involves a thin material that has no thickness approximately, and it is a triangular shape that resides in the XY plane. The shape itself has some surface density, so it's filled in. And in the problem, it's specified to be 24. Let me just note, 24 is unitless, and so there should be some units here. That's okay. We're just going to go along with it. The problem asks for a few things. One, it asks to figure out what is the inertia tensor, I. And second, it asks to figure out what are the principal moments and the principal axes. Cool. So let's write some things down. So the surface the surface density is given to be 24. We're only going to plug that in for part B. I'll keep part A generic. And the first thing that I would do if I were looking at this problem is to draw it out and figure out what does the shape actually look like? How is it that we're going to plug things in such that we can do the integrals necessary to solve for I? The shape looks something like this. It's given to you in the problem as well, and I forgot to mention this, that the three sides are 0, 1, 1, 0, and 0, 0 for the triangle. So this is the filled-in shape. What this means is that if you want the max height of the triangle, the max height is given as a function of x or y, depending on what you are parameterizing things in terms of 1 minus x is equal to y of x, or x of y is equal to 1 minus y. And so that's going to become relevant in the problem. Cool. So I'll keep the picture up for now as we are embarking on the problem. So to solve for the tensor I, there are expressions that are given in the book, and there's a few subtleties, I'd say, that come up here as a result of the setup of the problem. So like I said, this thin material only exists in the XY plane. So if we wanted to solve for the diagonal components first, we look at something like IXX, and I'll put in quotes that's equal to some sum over all the masses that you get times y squared times z squared. So these are masses that are located, the bits of mass for this object that are located at some y and some z. Because we have no mass that resides in the z direction, there is no term that looks like this for IXX. Also, the full mass, or the masses that we are dealing with, are actually dm's. This is equal to sigma times dA. So an integral over the infinitesimal area where the mass exists. Cool. So what that means is that IXX, instead of being a sum, should be an integral over dA times sigma times y squared. So the crux of solving this problem is figuring out how to express dA such that you can do the integral. And we can do it as follows, which is that there's going to be some integral from 0 to 1 over the x coordinates. if we take y to be a function of x, what we need to do is integrate from, let's say some point, let's say this is the x point that we're at, and integrate up to the y that represents the max y for the triangle at that x point. And so that is given by our expression y of x is equal to 1 minus x. Therefore, we integrate from 0 to 1 minus x over the y coordinates, sigma y squared. And again, y squared is really y squared as a function of x. For the first integral, we're just going to consider y to act as though it is some scalar, so that we just integrate 0 to 1 minus x. And so we end up with an expression in terms of x that gets output. So I can actually erase this. That's kind of confusing. We don't really need to consider y to be a function of x because it's just getting baked into the bounds of integration, 1 minus x here. Once we have an expression in terms of x, we just integrate 0 to 1 in the x direction, and we end up with a final expression. I'll leave it to you guys to do this out. The reason being is this is just polynomial expressions that you're doing. This should be a doable integral for you at this point. The answer, though, for comparison to your own notes is sigma over 12. So if we wanted, so that's ixx. If we wanted to figure out iyy, which is the next vertical component, sorry, diagonal component of the inertial tensor, it likewise is going to be independent of z, but in the case for iyy, it's not independent of x. So iyy is equal to sigma integral 0 to 1. This time we're going to be integrating across the y-axis and then integrating at some y from 0 to the max x value. So really we're looking at x of y is equal to 1 minus y, which determines the integration range for x. So we integrate over y last, integrate over x first. And this is exactly the same expression as we had before, but the variables are just switched, so we know this is going to come out to sigma over 12. Very good. So I'm going to erase this because we don't need the picture anymore to guide us for doing these integrals. Cool. So the last diagonal component is izz. And with izz, this is equal to, let me put stuff in quotes first. I think that's pretty helpful. You sum up over the masses that show up in the x direction and the y direction. And so if you notice these quoted expressions, this is going to be the expression for ixx with the sum, and this is the contribution, sorry, iyy, and this is the contribution to ixx. So in the case of this problem only, izz is equal to iyy plus ixx, so this is sigma over 6. This is not a generic expression, just to be clear. So lastly, and what makes these types of problems challenging is that we have off-diagonal components to take into account. And the only ones that we need to account for are the I, X, Y components. The reason being is that I, X, Z, and I, Y, Z involve Z's, and we know that we don't have any mass along, bits of mass along the Z direction. Everything is at Z is equal to 0. So the only non-zero off-diagonal term is IXY, and the tensor is symmetric, so ixy is equal to iyx. And in quotes, I'll put that this is equal to minus sum over alpha, m alpha, y alpha, x alpha. You can do this integral however you like. You can integrate over x first or y first. Just plug in the appropriate bounds for the rightmost integral that you are doing. So in this, I'm going to choose to do the x integral last and the y integral first. Again, this is a polynomial expression. I expect that you should know how to do this for the course. I'll just leave it to you to verify this comes out to minus sigma over 24. So all together, what that means is that we are not going to have a diagonalized tensor. I will write it out so that we can begin part B. So the generic expression for I is equal to sigma over 12, sigma over 12, sigma over 6 in the diagonals, and then any z components are 0, and then minus sigma over 24. So you might see why the problem said that we should plug in sigma is equal to 24. It makes the expression look very, very appealing. So for part B of the problem, it asks you to find the principal moments and axes. Finding principal moments and axes, that should ring eigenvalue problem to you. The way that you find eigenvalues and eigenvectors is pretty straightforward. It's the same every time. You take the determinant of the characteristic matrix. So my kind of scripted 1 is just the identity matrix. It is all diagonals of 1s multiplied by lambda. That's going to be the eigenvalues that we get. And so in this case, this is determinant of sigma over 12 minus lambda on the diagonals. And the off diagonal terms are minus sigma over 24 for the xy's, and then there's just zeros. And so to find the eigenvalues, we set this equation equal to 0 and see what the roots are for lambda. Those lambdas which solve this equation are going to be the eigenvalues. Those are going to be your principal moments, from which you can find the principal axes as the eigenvectors that correspond to those eigenvalues. So here it helps to plug in sigma is equal to 24 finally, because it's going to greatly simplify this problem so that you don't have a headache and want to rip your hair out and cry. So for sigma is equal to 24, we have that 0 should be equal to the determinant of 2 minus lambda, 4 minus lambda, bunch of zeros, and then -1, -1. Taking determinants, again, this is something I expect that you should know how to do from linear algebra. One way of doing it is to take the following approach, where we take this number and multiply by the determinant of the 2 by 2 matrix here. So that's 2 minus lambda times 4 minus lambda. That gets multiplied by 2 minus lambda. Pretty straightforward. And then we take that and subtract from this number times the determinant of this smaller matrix here. So we have -1 times -1 multiplied by -1 times 4 minus lambda. And then the other contribution to the determinant is trivial. So therefore, what we get for an expression is 2 minus lambda squared times 4 minus lambda minus, in parentheses, 4 minus lambda. We can combine this into 2 minus lambda squared minus 1 times 4 minus lambda. And if you expand that out into lambda squared minus 4 lambda plus 3 multiplied by 4 minus lambda, the roots of that are 1 and 3. Therefore, this is 1 minus lambda times 3 minus lambda times 4 minus lambda. That means your principal moments are 1, 3, and 4 for this problem. Now it's a matter of figuring out the principal axes. So I will erase this. And like I said, finding principal axes, once you have the eigenvalues, it turns into a problem where we plug into the characteristic equation each lambda, and then we find the vector that is normalized and solves the characteristic equation that is non-trivial, so non-zero vector. So lambda 1 is equal to 1, lambda 2 is equal to 3, and lambda 3 is equal to 4. So for lambda is equal to 1, we have I minus 1, because we plugged in lambda is equal to 1, times some omega vector is equal to 0. For our problem, that means solving the following. We subtracted 1 off the diagonal. This is the set of equations that we need to solve for, which reduce to omega 1 minus omega 2 is equal to 0. And this happens twice. And then omega 3 is equal to 0 is the last equation. That's the easiest to solve for. For the other two, they're the same, so they should be set equal to one another. Basically, omega 1 has to be equal to omega 2. Pretty straightforward to solve for that equation. The normalized vector, so basically take the dot product of whatever vector satisfies those equations and set that equal to 1, is going to be the following. So E1, the principal moment, so this is the principal axis for the principal moment 1 is equal to this. And likewise, you can go about and solve for the other principal axes for each principal moment in a similar fashion. You're just going to get a bunch of equations that you need to solve for, and once you plug in the correct lambda value, you get the correct equation to solve for the different components of the principal axis. And again, all you need to do is normalization. And here they are for your reference, but I'll leave the last two up to you. So that's all I have for the example problems. Let me know if you have any other questions, and I wish you luck with the exam.